So we continue chapter 30, talking about mutual and self-inductance. Now this is a little bit different order than the book does it, because the book does self-inductance first, then mutual inductance. But in lab we did mutual inductance. I thought it makes sense that I talk about that. So imagine, for example, that we have a circuit, and the circuit is simply a switch, power supply, and resistor. So if you close the switch, then what happens is current starts flowing. Well, if current starts flowing, then that means by the right-hand rule that there's going to be a magnetic field into the screen on the inside of this and out of the screen on the outside. Again, curl your fingers in the direction that current is flowing in the circuit. So current's going to flow this way in the circuit, and so your thumb points in the direction of the magnetic field, so into the page. Well, what if there was another circuit inside here like that? Now, before you turned on the current, there was no flux in there. Then you turn on the current, and now there's a flux. And so we know from Faraday's law that a change in flux is going to produce an EMF. So the EMF here is minus the rate of change of the flux. Your book puts an N in there also to indicate that it's possible that this could have like multiple loops in there. Okay, so that's the EMF, so that's Faraday's law. Okay, so we look at this and we say, well, even though that other circuit's not connected, it has an EMF when you close the switch. Now, once the switch has been closed for a while, then what happens is that the current steadies, it quits changing, and so the flux quits changing. And when the flux quits changing, then no change, the derivative is zero, so the EMF is zero. And so that's something that you observed in the lab when you did this. So let's consider this, that this is Amperes Law down here, and if we imagine here that this is Amperes Law, okay, and let's look at this and say, well, we're looking at the rate of change here, and we know the flux is going to be proportionate in some fashion to the current. So the flux has got, in some way, the flux is going to be proportionate. So we want the flux inside of here. So the flux inside of there is going to be proportionate to the current. It's going to be related to the number of turns in that second loop, call that loop 2 and that loop 1. And it's going to be related there. This is the flux 2 due to 1, okay? And so that's going to be proportionate to the current. So we can say the proportionality is something that we call the mutual inductance, okay? We've got that the mutual inductance, okay, is times the current is going to be related to or equal to the number of turns in that loop times the flux in that loop due to the other one. Well, we look at that, we say, wait a minute, if I have minus ddt of both sides right here, okay, so then what that would do is, well, on the right here, minus into the derivative of the flux. On the right over here, we're assuming that this thing that we call the mutual inductance can come out of the integral. It's constant. It's going to be the same relationship to, you know, as long as you don't change the orientation of everything. Okay. Well, what's on the right over here is simply the EMF. And so that's the EMF. So we can say that the EMF induced is minus M di dt. So the rate of change of the current is directly proportionate to the EMF induced in the secondary circuit. The proportionality we simply call the mutual inductance. Mutual inductance is purely geometric. It depends on how the two circuits are shaped, depends on the size of the circuits, depends on how many loops are in the circuit, depends on how the circuits are oriented at each other. One circuit produces a magnetic field that produces a flux in the other circuit. Okay, so this is how two circuits interact with each other. So this is mutual inductance. But consider just one circuit all by itself. So we have just one circuit all by itself right here. And that circuit has no current in it because the switch is open. So if you close the switch, current starts to flow. If the current starts to flow, right-hand rule, you have a magnetic field inside the circuit. So that means this entire circuit, even without anything else, has a flux through it. Well, we know that EMF was minus N minus N derivative of the flux. Okay. Well, by the same token, we can say that the flux is obviously got to be proportionate to the current. The bigger the current, the bigger the magnetic field. The bigger the magnetic field, the bigger the flux. So we can do the same thing. We can say that the flux is proportionate to, so let's say that the flux here is proportionate to the current. Well, the proportionality we're going to call the self-inductance, and that also is going to depend on how many loops are in the circuit. Because I can imagine a circuit in which instead of just drawing it like that, I have here comes down like that, and then we make like several loops here before we come back and connect. And so that's going to have more flux in it because you have more loops here collecting the flux and magnetic field going through more loops. And so once again, up here, if I take negative derivative of both sides, then so minus ddt of both sides of this equation, the one on the left is the EMF, and so that's going to be minus L di dt. So that's the EMF of self-inductance. Now, every circuit is going to have a self-inductance. So that means that when you first turn on the switch for any circuit, when you first turn on the switch, what's going to happen is the current as a function of time is initially going to be 0, and it's going to rise up to some stable current. And so there's some finite amount of time here in which the circuit has not yet reached its full current. And that depends on the circuit. The less self-inductance the circuit has, the quicker it reaches its equilibrium current. The more self-inductance it has, the longer it takes to reach the equilibrium current. So every circuit has that little bit of time lag in there. Well, there are times you actually want a circuit to have a huge time lag. In other words, it does not respond very quickly to any kind of change in current. For example, like a lightning arrestor or something, or any kind of surge protector. And so what you would do is you can imagine taking a circuit and just taking part of the circuit and making it into a tight coil, and then it goes to something else right here, like a resistor. And so this part of the circuit is going to have huge amount of self-inductance compared with the rest of the circuit. In fact, the rest of the circuit is going to be negligible self-inductance compared to that one circuit element right there. And so that circuit element right there, we would simply call an inductor. In fact, the symbol for an inductor is basically that which we saw in the lab, and so that symbol for an inductor symbolically indicates that you've got a circuit element that has a large amount of self-inductance in it. And so that's our next part. The last part of this chapter is how do inductors behave in circuits.